management and resilient efforts using satellite data from the Copernicus program. This is open access Earth observation data that is provided by the European Union and the European Space Agency, where I'm from. This is from the inside of the ISS. This initiative, CopPhil, is managed by the European Union's delegation to the Philippines, and it's being implemented by ESA. And we are carrying this out in partnership with our Philippine colleagues, the Philippine Space Agency, PhilSA, and the Department of Science and Technology, DOST. CopPhil is funded by the European Union under its Global Gateway strategy, which is a strategy to promote sustainable investments and international partnerships in sectors such as health, education, but also research and development. The strategy aligns with these global goals, such as the United Nations Agenda 2030 and the Paris Agreement. Right now, CopPhil is focused on working on the key infrastructure projects, such as the Copernicus mirror sites and the services that build on top of this. So these three services are the ground motion monitoring service for detecting seismic activities, volcanic eruptions, and landslides. There's the coastal marine habitat monitoring, or benthic habitat monitoring, to assist sustainable coastal management on detecting coral bleaching events and mapping the depth of the ocean. Then lastly, we have the three different land services, the land cover, forest, and crop mapping, which is for the forest monitoring we are here today to support environmental management, biodiversity, and conservation. So these services are being and have been co-developed together with the local stakeholders and mandated agencies in the Philippines. This is to ensure that these services meet the specific needs of the Philippines. And CopPhil prioritizes this training and knowledge transfers to make sure that these services remain practical and sustainable even after the initiative ends. So thank you for your attention, and I look forward to your participation today, and I hope you have a good training session. Thank you.
Thank you, Casper. So again, today we begin the forest monitoring training series. And yeah, Patricia, you can also start sharing your screen. So again, the forest monitoring training series, part 1 fundamentals, will introduce the key concepts and methodologies for observing and analyzing the forest areas. And this training will build on the foundation for the forest monitoring session later on. And we're very glad to have us here, Patricia Perez Ramirez from GMV, who will be leading today's session. So she's Patricia and her team with Pablo and Angel, one of the main service providers under the CopPhil for forest monitoring, and brings their experience and extensive for applying EO data for forest-related applications. So floor is yours, Patricia. You're ready?
Can you hear me now?
Yes.
I'm so sorry. I have some troubles with my Teams, and I don't know if you can see me, but good, at least you can hear me. I'm so sorry for that. I don't know what happened, but Teams doesn't want to work for me today. I'm so sorry for that. I will share my screen.
Yes, all good now.
Can you see it?
Yes.
Perfect. So let's see. Okay. Well, as Carla said, my name is Patricia Perez, and I work at GMB Spain, which is a tech company. My colleague Pablo Jesus and Angel Fernandez and I work in the remote sensing and geospatial analytics division. We are in charge of the forest products in the CopPhil project. and I will give an introduction to this training theoretical course today, and I will show a little bit some details about the 3 training courses that we will have for forest. And then I will show the agenda for this session. And then we will have a short session with questions that we will like to ask you before starting the meeting to know some to know if well, the knowledge that you have before the meeting. So I will start with the calendar that we have for the training session. Today is the theoretical course that we will have we'll give some concept applied to the forest uses, and this is in an online mode. Then we will have a practical training course in May, the last week. This will be on site in the Philippines. We need to further plan the specific dates of this training session, but will be in the last week. We will give you more details in the coming weeks for this practical session. And we will have a final one related to application for forest that will be online probably. And this will be in the first week. This probably will be yes in the first week of August. Then what we have for today. Now we have already the welcome introduction. Now we are with the motivation overview. We will see the question that I have already mentioned, and then we will start with the content of the training session. The 3 well, 4 blocks of content that we will have for this session will be led by my colleagues Pablo Jesus Torre and Ángel Fernández, that are both experts on remote sensing applied to forest. So we will have a first session related with the principle and data with basic concept. We will see the optical radar and LiDAR sensor applied to forest, and then we will see a session with the data analysis when they will explain several techniques, the artificial intelligence algorithms that are used in forest. And we will also see something about validation, and then we will finish with CopPhil, with the CopPhil forest products. Well, they will explain what we have done for this project, and then we will finalize with a few examples with other application for forests. And then at the end we will have a part of the session with conclusion and final question. We will use the same tool that I will explain right now. So now the idea is that you can connect to the Mentimeter tool. I will share the link in the chat as well. You can join with the QR code if you prefer, or you can enter to menti.com and enter the code that appear here. I already shared the link in the chat, so you can start joining in. When you access to this tool, you will be asked to provide your name. It's not needed that you provide your name. If you don't want, you can provide your institution, affiliation, whatever, your name, both. This is not needed, as I said, to provide the name, but something that can be, this is a requirement to enter to the question session. So if you have any trouble to connect, please let us know. If not, I will show the question. Let me put it here. I hope you can see it, and I will start with the first question. Let's see. Here I can see if people is replying to that. Well, the first question is, have you attended a land cover theoretical training course, or have you completed it on the Moodle platform? As Casper mentioned, Forest is part of the land cover forest and crop pilot service of CopPhil, and the land cover theoretical training course was carried out in February, and the information of this course was uploaded to the Moodle platform, and they already provided in the course a lot of material related to the basis for remote sensing. So I think it is a good start for the training course, and a good basis to do it before this training session. So that's good. Many people already attended the course or completed on the Moodle platform. Okay, I think that we can move. Okay, we'll move. So most of people already did it. This kind of question help us as well to know what are the knowledge of the attendees, and even the content of the course is said, but perhaps we can't emphasize some aspect more than other. So in this second question, what we would like to know is your level of knowledge about remote sensing and your data related to the land cover and forest applications. Okay, basic, intermediate. We will give in the course today some basic content, but the idea is that to provide then apply to forest. Okay. We had in the previous one, didn't, so let's wait for a few more answers. Okay, that's good. Okay, we will move to the next one. Here, would like to know what is your main goal in participating in this course. You can click more than one of the options that we are providing. Perhaps you want to improve your knowledge on remote sensing, or on artificial intelligence, or both, or perhaps you would like to improve your knowledge on forest application or apply to some projects or even others that are not here. Sorry, I pressed something. I put others, so maybe in the last question that we have after this one, you can say another goal that you may have. Okay, many different goals. That's good. So we will move to the next one. And finally, we would like to know if you have any other comments before starting. So you can give here, this is an open question, give here your opinion, what you expect for the training course, or what would you like to learn, or also you can give your comment in the chat if you prefer. That's good. Yes, I did also to give the course as well. And then we will have another set of questions to know what you think about the course, after the course. Okay, I think we can start. I will keep this open in case you want to say anything else. You will read that, and I will give the floor to my colleague Angel, so he can start with the content. So Angel, if you want to share your screen.
Okay. Well, actually, I cannot share my screen because Teams says that only meeting organizers and presenters can share. So
okay, give us a minute.
Maybe, okay, maybe someone has to change my role or Well,
yes,
good
should be good now.
Okay, now, yeah, perfect.
Okay.
Perfect, yeah, now I can. Fine. Okay. So, well, good afternoon, everyone, or good morning if you are in any other place that is not the Philippines. Well, my name is Ángel Fernández, and I work as a remote sensing specialist at the Remote Sensing and Geospatial Analytics Division at GMV. My main focus is remote sensing and machine learning and deep learning forest applications. And in CopPhil, I have been together with Pablo behind the main technical development of the forest products. So I will give you the first part of this, or the first parts of this training, which are some basics applied to forests, and then later Pablo will talk more about data analysis and algorithms. Okay, so I know some of you already were present in the land cover training sessions, but just a brief reminder for those who were not there. Just what is Earth observation? Or we have to distinguish between remote sensing and Earth observation. They are basically the same, but remote sensing is just the science of deriving information from measurements made at distance, typically from satellites, but also from aerial platforms or whatever. And Earth observation is specifically applied to monitor Earth system materials and processes. Well, I think all of you already know this. So this the main three technical parameters defining a remote sensing measurement are the spatial resolution, spectral resolution, and temporal resolution. there are also some others. So as I know that you already saw this in the land coverage training session, I will pass quickly these slides just to give a brief introduction. The spatial resolution is the size of the pixels. Basically, you can see here a 5-meter resolution image versus a 60-meter resolution one. The spectral resolution is the width of the spectral channel. And lastly, temporal resolution is the time that passes between each imagery acquisition. So you can see as the satellite, this is Sentinel-2, for example, how the orbit is going and is catching images. So every number of days, normally 5, it takes a new image. So these are the main 2 types of sensor. There are many types of them, but the main one, we can say that we can classify them in passive instruments and active instruments. Passive instruments, well, they are characterized because the radiation is only received. So it is typically reflected from the sun in the surface of the Earth and going to the satellite. So these are the, for example, all the optical imagers, the multispectral and hyperspectral instruments. And on the other side, we have the active instruments that can emit and receive radiation. So, for example, the SAR sensors or the LiDAR sensors, they emit the radiation, which is then later reflected on the ground and comes back to the sensor. Well, let's see a bit more in detail the optical sensors in Earth observation and the application of optical data to forests. Well, basically, we can say that optical sensors are those who are receiving information from the optical region of the electromagnetic spectrum. So this is from 400 nanometers to 2,500 nanometers, more or less. This includes the visible light, blue, green, red, normally, all the colors that we can see with our eyes, the near infrared spectrum and the shortwave infrared. Well, it's important to say that these are conventions, these names. Sometimes we can find some difference in what we consider near or short infrared, but this is a well-known standard, and it's usually used to name the different bands of the sensors. Well, the spectral signature is basically the variation of reflectance along the electromagnetic spectrum that characterize each material. So yeah, it is the basic characteristic of materials that help us to discriminate all of them using remote sensing, using optical sensors in this case. So you can see here as, for example, I don't know, vegetation has a response in the near infrared here, while, I don't know, snow in near infrared is higher or whatever. Okay, how is the spectral signature of vegetation and of forest, of course? Well, a green leaf has this spectral signature, a healthy and green leaf. So the different pigments absorb radiation in all the visible spectrum, but especially in the blue and red parts. So for that reason, we see it in green, because it's where the most energy in the visible spectrum is reflected. But if we could see in near infrared with our eyes, we would see another color, because then the higher reflectance of the green leaf is on the near infrared. And then, well, in the shortwave infrared, there are some water absorption bands, and well, the signature here is more changing. So you can see here, for example, a healthy leaf has very high near infrared and a relatively high green. When the leaf is stressed, it loses the cellular structure, which is what made near high, so it loses the near reflectance. And when the leaf is dead, you can see it like in brown, because the three colors are already mixed and there is no structure. So, okay. So we can use this spectral signature using multispectral sensors by building or computing color composites. This is just a way of visualizing the data. So we can see in blue, green, red. So everything that we see is an addition blue, green, and red components. So if we assign the different bands of the multispectral sensor to these colors, we will see the image in one or another color. For example, here we have two images. In the left, we can see the vegetation in very intense green, and on the right picture, we see vegetation in red. Why? So you can see here the spectral signature of different materials, but well, in special of vegetation. And here in this image, we have assigned the blue channel to the the blue channel to the red part of the spectrum, the red channel to the so the sphere channel to the red part. Sorry, the red channel to the sphere part of the spectrum, and the green channel to the near part of the spectrum. So as vegetation is has a more intense radiance reflectance in the near region, we see the vegetation in green. That's all. In this case, we have put the near infrared in red, so we see the vegetation in red. So it's just a way to let's say highlight some characteristics of the image, so to be able to better distinguish vegetation and other plant covers. I think you already saw some of these spectral indices in the plant cover course, so I will give a brief introduction. So the spectral indices are mathematical combinations of these spectral bands, so allowing just to assess specific characteristics of the land cover. We usually, mainly in forest application, we use vegetation indices, which are used to monitor vegetation status. The most known vegetation index is, of course, the NDVI, the Normalized Difference Vegetation Index, which has been related to vegetation health, primary productivity, photosynthetic activity, and other key parameters of vegetation. So it is based on near reflectance, which is related to healthy leaf structure, and red reflectance, which is related to the low chlorophyll content. So we just build normalized difference, and higher NDVI indicates healthy leaves with chlorophyll, and lower NDVI indicates that something is going wrong with this vegetation. We can see here in a tree, for example, how the radiation is reflected when the tree is healthy and the NDVI is low, 0.72, and here the NDVI is, so here is high, sorry, and here is low because, well, the tree is dying, or it is a deciduous tree, but vegetation is not green and healthy. Another interesting vegetation indices are, for example, the modified soil adjusted vegetation indices. There are many versions of these soil adjusted vegetation indices. The important thing is that they are used to minimize the effect of bare soil in the pixel. So when we see a pixel, it's not typically only vegetation, but also the reflectance has some contribution of the soil. As you can see here, the NDVI has some problems with this, so it varies depending on the type of soil that we have behind below the vegetation layers, and SAB is more robust on those cases. And also another problem of NDVI is that, well, it's a very good index, but it saturates relatively soon. So if the vegetation is very dense, very green, it tends to reach a maximum value, get stuck there. And SABI is much more, let's say, progressive and don't get saturated so easily. Another example, just to show you that you can build specific vegetation indices or indicators using empirical models. For example, this was one case made by the University of Valencia here in Spain to relate the Sentinel-2 data with the leaf area index, which is a biophysical parameter that can be measured on the ground. So they build this formula and applying a coefficient. They adjusted this model, and well, even when the adjustment is not very impressive, let's say, but it's still quite good. And well, it's just a fast way of having an idea of what is the leaf area index of some vegetation. This is another example. So we have specific vegetation indices for specific types of vegetation. In the Philippines, for example, it is very interesting to use mangrove vegetation indices. There are many of them. We have, for example, the MVI, Mangrove Vegetation Index, which takes into account mainly the greenness and the moisture, which is related to the SWIR, to the shortwave infrared, to differentiate mangroves from another forest. So you can see here, for example, in the image, many types of vegetation with mangroves, and in green, the index, the MVI, the values of MVI, and you can see that there is, so the difference with respect to other types of vegetation is clearer using the MVI. So you can see here, as it maximizes the difference in the region where mangrove can be discriminated from other types of forests. So we have also the these mangrove indices. There are a lot of them. And well, just to finish on vegetation indices, there are not only vegetation ones, but also bare soil indices, burnt area indices, indices, whatever. Bare soil indices, I would like to mention the bare soil index and the modified bare soil index, which are quite good to distinguish soil from other types of land cover, for example, vegetation, and the burn area indices that are widely used in all the forest applications of remote sensing to not only to detect and map burned areas, but also to derive burn severity. You can see here as not only the perimeter of the fire was delimited, but also these indices allow to assess the severity of the fires. Well, just to give a last overview on a technique used for optical remote sensing in forest, we have the spectral mixing, which consists basically on considering that each pixel is not pure. So in each pixel we have contributions from different surfaces, vegetation, soil, water, whatever. And so it takes the spectral signature of each pure material, this pure spectral signature of vegetation, pure spectral signature of soil, for example, and it separates the digital values of the pixel in, let's say, in proportions of the different contributions. So this is usually used in hyperspectral sensors, which don't have, let's say, discrete bands as the multispectral sensors, but they have many bands and it's almost continuous. So as you can see here, these are spectral signatures derived from hyperspectral sensors. But well, this technique can also be used in a simplified way using multispectral sensors. So the main applications of this is, for example, mapping two species. We consider that some species has a specific pure spectral signature. We can see how close to this signature is the pixel and how close to another signature is the pixel, and then compute the different the main species present in each pixel. And another application is for health issues. We can see how the spectral behavior of some area is deviating from the let's say the normal one, and then assess the health status of the vegetation. Well, until here, the introduction for optical sensors. I hope you don't get bored. Now we are going to talk a bit about radar sensors. So yeah, I will give a brief introduction. So radar sensors are those who emit. These are active sensors that emit and receive radiation in the radio part of the spectrum. So with wavelengths typically longer than 1 millimeter. Okay, so these are the main bands used in radar remote in radar remote sensing. As you can see, for example, the wavelength of the X band is between 2-3 centimeters, but in the P band, the wavelength is huge, is even longer than a meter. So the wave is really big. So the main characteristic, let's say, or at least the star characteristic in remote sensing of the radar sensors is that they are not affected by clouds, as waves can penetrate the clouds and go to the surface of the Earth, given this long wavelength. Well, an important thing is that we will see the name SAR instead of radar. SAR is simply a synthetic aperture radar. Is the kind of radar that is normally mounted on satellites. Well, as I said, the radar signal is emitted from the satellite and then received back, and as you can see here, and the signal is an electromagnetic wave with the three main components that all waves have, which are amplitude, which is directly determined by the energy of this wave. These are the characteristics that we will normally use, or at least more usually. The phase, which is the position of a point in the waveform cycle. So it can be in the top of the wave or in the bottom of the wave, and it varies from 0 to t. and the polarization, which is the orientation of the electric vector defining the wave. Okay, the polarization can be vertical or horizontal. You can see here so this will be a vertical polarized wave and this an horizontal polarized wave. So it's important to know that the reflected signal is expressed in complex numbers. So it's a very complex data before pre-processing, because it has the amplitude part, which is real, and the imaginary part, which is the phase. So how does the radar backscatter interact with forest? So we have three main types of backscattering in forest: the top of canopy backscatter, which is this one. So the top of vegetation reacts to the radar beams. The volume scattering, which is directly related with biomass, and the double bounce scattering, which, well, depends on vegetation. It's just, as its name says, it's double bounce scattering. So it's very important to say that this backscatter depends heavily on the wavelength. So backscatter depends on penetration, which is directly related to wavelength. So, for example, the X band interacts mostly with the top of the canopy and cannot penetrate much deeper because it's shorter wavelength. And you can see, for example, the L band, which is widely used for forest applications because it can penetrate the leaves and so give much more information about the forest, the forest and the trees. So this is how we would see a forest, well, a tree, if we could see with radar eyes, let's say. So as you can see, the X band, we can only see the leaves, and the L band, we can already start to see the structure, and the P band, for example, we see the trunk and the main branches. Okay, just to have a general idea of how it works. So a very important thing is that, as I said, the volume backscatter is highly related to biomass. So this is one of the main applications of radar remote sensing to forests. So higher biomass increases radar backscatter due to greater surface that interacts with the radar beams. Longer wavelengths, as I said, penetrate deeper. So, for example, the L band can interact with through trunks, branches, and so on, while shorter wavelengths, as C band, mainly reflect from leaves, so it's not so suited for biomass estimates. The different polarizations also have an influence on the relationship between backscatter and biomass. The cross-polarized signal, so HV, it's horizontal vertical. It means that the sensor is emitting in horizontal polarization, but it's receiving the radar signal in vertical polarization. It's so the cross-polarized is the more sensitive polarization to biomass. And, well, a limitation of this is that at high biomass level, the signal saturates. So, and we cannot, so for example, in tropical, dense, aged forests, we cannot be so precise. So the saturation is lower at large wavelengths. So, for example, here we have a comparison between L band and P band. And as you can see, so the P bands normally allows higher, a better estimate of above ground biomass. Then, well, the relationship of backscatter to biomass is just built on typically on empirical models or regression models, assigning coefficients to the different polarizations. And as you can see, the R squares are quite high, 0.7, 0.8. So it's a good way of estimating biomass. So the typical problem there is that we need relatively detailed field data on a background biomass to calibrate the models, and we normally don't have them. But if we have them, very good models can be built. Well, so then if radar is so good for forests, because it's really a good thing, why don't we use it more? Well, radar has several, I would say, strong limitations. The first of them is the topography. So the radar looks aside, as you can see here. So the sensor looks in a oblique direction. So this creates different undesirable topographic effects. Mainly, these are three effects that are the layover, shadow, and the foreshortening. So the layover occurs, you can see the layovers are the areas that where the slope looks to the opposite side of the sensor. So yes, the foreshortening is when the slopes look towards the sensor. So you get these illuminated pixels here in white, very bright. And of course, there are shadowed regions. So if the topography is really steep, actually the sensor cannot see what's behind the mountain, and you get series of pixels without data. So this is there are several methods to correct these effects, but still with this, well, it's a strong limitation. Another limitation is the speckle. So the reflected energy of the radar signal is combined as a vector addition, not as a scalar addition. So it's an effect of the coherent illumination. So basically what you have to know is that this translates into constructive and destructive interferences that leads to speckle. So you can see here how this how the signal the value of the pixel is built. So each object in the pixel makes a different contribution in a different direction. So the effect is that we always have some degree of speckle, which is this salt and pepper noise, which makes hard to work with the image. And well, the third limitation I will mention is the well, the water effect or the moisture effect. So, well, this is caused by the dielectric constant of water. So the dielectric constant is a measure of the material's ability to store electrical energy. Most dry materials have a low dielectric constant from 3 to 8, more or less, and the water has 81. So it's very high compared to other materials. So what happens that well, the electric constant increases the backscattering potential. So the consequence is that when the soil, vegetation, when the land surface is wet, the signal varies a lot. So for example, you can see here 2 corn fields in the United States. And you can see the irrigated one and non-irrigated one, and how the signal is totally changing. So you have two. I always say that we are very happy to say that radar is not affected by clouds, but then it is very affected by rain and dew. So we have to take this into account. Well, I won't after the basics, I won't go deeper on this technique, but just for you to know that this exists. So the SAR interferometry is widely used techniques for several applications. It is based on using 2 or more consecutive radar passes to measure surface changes. So it is so what is analyzed in this case is not the amplitude but the phase of the radar signal. So the main applications are for earthquakes, landslide monitoring, glacier movements, infrastructure stability, and so on. It has been used for forest, but it's not a typical application that can be used for forest. And well, another interesting technique is the polarimetry, that it's similar to the let's say color composites or even to the spectral mixing in optical remote sensing. It analyzes how radar signal in different polarizations interact with different land covers and surfaces. So it's just this. It's used for land cover and vegetation classification and many other applications. The main problem with this is that to really apply good polarimetry techniques, we need full polarization. It means we need horizontal, horizontal, vertical, vertical, horizontal, vertical, vertical, horizontal. So we need all the combinations of the polarization, or what we call quad pole. And typically, at least in satellite sensors, we only have dual pole. For example, in Sentinel-1, we have the vertical, vertical, and vertical, horizontal. With this, the polarimetry is very limited. Last, I would like to mention some vegetation indices that are used in the SAR world. The principles behind this are the same than for the optical vegetation indices, but in this case, we will use polarizations instead of spectral bands. The first one is a radar vegetation index. So originally it was proposed for quad pole. So you can see we have HV, HH, VV, and HV. But it has been adapted to Sentinel-1, for example, to dual pole by transforming some of the parts of the formula. So the value goes from 0 to 1, where 1 is dense and dense vegetation, and 0 is no vegetation. This doesn't work as well as the optical vegetation indices. So the data is much poorer. So, well, it's just an ancillary data that can be useful, but it has not the biophysical significance that we saw in the optical based indices. Another index is the radar forest degradation index, the RFDI, which basically considers the difference between horizontal, and the cross-polarized channel to, let's say, give an indicator of the degradation of the forest, where low values are typically dense, healthy forest, and above 0.6, there is no forest, basically. Okay, just to end with the basics of remote sensing applied to forest, I will explain some of the main characteristics of LiDAR. I think, well, I'm not sure if you saw LiDAR in the land cover session, but well, this is very, very short. Well, LiDAR means light detection and ranging. So I didn't say it before, but radar means radio detection and ranging, because the sensor emits radio waves and receives radio waves. So LiDAR makes the same, but with laser, basically. It emits laser pulses, and by computing the time from the emission to the return, it can compute distances. So the main consequence of this is that LiDAR can measure the structure of vegetation directly, because you have exactly the height of the tree or whatever. So there are mainly two types of LiDAR sensors. The first one is the continuous wave. Yeah, the changes in phase are used to compute the return time. So they have the advantages that of having a large swath, so large footprints. These are the sensors typically mounted on satellite platforms. And then we have the discrete return LiDAR that is by far the most widely used for forest application, that it directly registers the return time of the laser pulse. But it has several problems. Well, the main of them is that it has a small footprint and it's mostly mounted on aerial sensors, as you can see here. So the continuous wave, as I said, well, you can see here how this works. So it registers all the energy reflected by surfaces in the vertical dimensions in the, let's say, in a whole footprint. And well, the problem of this is that there are few systems for vegetation monitoring, and these are normally experimental. Some examples would see all of this. For example, the ISAT that is was built for ice monitoring. You can see how it works. So it takes different measures, different, let's say, samples of LiDAR data. So, but as I said, for forest monitoring is still quite experimental in most cases. Then we have the discrete return that is it's widely used on forest applications. So it records the data as X, Y, Z points. So the density of points is very, very high normally. And well, it records the multiple returns for each transmitted pulse. So let's say when the pulse arrives to the top of canopy, the sensor receives a first return. Then if there is, I don't know, some understory shrubs, then the sensor receives a second return, and then with the soil, a third return when the laser arrives to the ground. So most commercial LiDAR systems are well, use this type of LiDAR, and it's very used for forest. You can see here an example of how this is Central Park in New York. You can see how the result after some quite a lot of preprocessing, how this looks like. This is a cloud of LiDAR points, and you can see the vegetation as it's very clear. So in forests, LiDAR can be used to measure, for example, height and structure. As I said, the LiDAR is a direct measure of the structure of vegetation in this case. So it can be used to estimate not only tree height, but also crown size, vertical structure, and so on. Also, it is used to enhance the typical inventory parameters, DBH, canopy cover, stand density, and the most important, I would say, is its ability to to be used to estimate biomass. So in a similar way than radar, with the difference that LiDAR is much more precise and don't have the, let's say, geometric and physical limitations of the radar signal. So the LiDAR points can be used to directly measure or estimate, not directly measure, but estimate above ground biomass and carbon stocks. So then again, I say, if this is so good, why don't we use it every day? So the main limitation of LiDAR is the high cost. So as I said, the satellite platforms are not so suited for vegetation studies for the moment. And aerial LiDAR services are expensive, zero price aircraft, sensors, pilot, of course. So these are costly. Also, the limited temporal coverage. So if you fly aeroplane with a LiDAR sensor today, we won't have it again in 5 days and 5 days as the satellite sensors too. So you have to fly it again, or so this makes it less suitable for forest applications. Well, as I said, the satellite sensor has have lower resolutions and limited coverage. And also, it is very important to consider the data and processing complexity. So we usually have a huge clouds of points, and processing LiDAR data usually requires advanced processing techniques and a powerful machine, and this is also costly. Okay, so this is all from my side. I hope you could learn some of the basics of Earth observation applied to forests. And now I will leave you with Pablo, with my colleague Pablo, which will introduce you on different data analysis, machine learning techniques for forests. Thank you, Pablo. If you want, you can take control.
Can you hear me?
Yeah.
Yes.
Yes. Okay. Good morning, good afternoon, everyone again. Well, my name is Pablo Torres. I work at GMB, the same as Angela and Patricia. I work in the remote sensing and geospatial analysis division of the company. Well, I used to work, or a kind of expert. I don't like to say the word expert, but I work with Earth in Earth observation, in the field of Earth observation, applying these different techniques mainly for forestry and forest health, but also in other fields as agriculture or climate studies. So today in these slides, I'm going to show you some different things. I'm going to start with some statistical methods. It's not the full picture of the different statistical methods that can be used to this kind of studies, but there are some of them that I want to show you that are mainly applied to this kind of issues. After this statistical section, I'm gonna explain how we have applied some of the methods to perform an analysis and to get the products of forest area and type, tree cover density, and forest change. The different methods I'm going to show you, and after that, if we have enough time, I will show you some other different products that we have generated in other other times in other projects. But it will be a brief introduction to other projects. So I'm going to start with the statistical session. Let me know if you can see my screen, please.
Yes, I think I can see it.
Can you see it full screen?
Yes, we can see.
Nice. So, as I said, I'm gonna start with some statistical techniques. This is not the full picture; it's just a snapshot of different statistical techniques applied to the field of Earth observation and forest applications. And the first one is, well, there's a bunch of different techniques, but they are grouped in the descriptive analysis at mean, median, mode, the standard deviation, as I'm sure all of you know these kind of parameters that you can get. The descriptive analysis is a type of data analysis that is focused mainly on summarizing and interpreting the data to make it understandable and to have a picture of what kind of data are you working with. This kind of analysis it doesn't give you predictions or they don't find the cause or the relationship, but they give you an insight into the different patterns or trends that you can find into the data. Well, then the next one, that is the correlation or regression analysis. There are two different, the correlations, for example, measures the strengths, but also the direction of the relationship between two different variables. But correlation doesn't give you the cause of this relationship. And in the case of regression, on the other hand, you have different models that can give you the relationship between a dependent variable and one or more different independent variables. Then this kind of analysis can give you some information to predict based on the raw data that you have or the observed data that you have. So the next one is the inferential statistics. You have samples, confidence intervals, hypothesis testing, but this one is a branch of statistics that gives you the opportunity to make conclusions or predictions, generalizations based on a sample of the data. And the fourth one is a kind of statistical techniques called time series analysis that used to analyze the different data collected over the time. And this is very important and is different from the others, but it considers the temporal order of the observations when they have been taken, and it could be useful not just for knowing how a variable varies during time, but also it's useful to know the future values to do some kind of forecasting. So this is just a snapshot of these classical statistical techniques, and opposite to this classical statistical analysis, you have machine learning, and machine learning is a branch of the artificial intelligence that gives you the opportunity this kind of algorithms gives the computer the opportunity to learn different patterns from the data that you give to the algorithm, and they can take some make decisions or predictions without giving the direct orders or explicitly program the algorithm to do it. So it's separated in different branches depending of the things that you want to do or the kind of data that you have. The first one is the supervised learning. Sorry, and this is a type of machine learning when the algorithm is trained with a labeled dataset. What does it mean? This means that the input data comes with a label or with a part of the data that corresponds with and is directly related with the other variables that you have it, and you can use supervised learning algorithm to do some classifications that is based on categories like colors. For example, you can see here in the picture is to separate between the colors based on a set of variables that you have given to the algorithm. But sorry, you can also do a regression analysis. Instead of having classes, you have a continuous set like a number. You can estimate. Well, an example could be estimate the temperature of a room. That is a continuous value. Well, moving to unsupervised learning, this is a well, we had supervised that you have data that is leveled, but for unsupervised machine learning, you have data, but this is not labeled. So the main of this kind of algorithms is to find different patterns of structures within the data or relationships without knowing this kind of relation, and that could be this kind of level. So it's used to explore the structure of the data. You have different things that you can do, like clustering is agroupations. Dimensional reductions is when you have a lot of variables. You can find the relationship between them, and you can reduce the number of variables. But it also you have another way of using unsupervised algorithm, like association. Like have an example, like you can give a lot of data of the different meal recipes, and you can find the common ingredients that I use to prepare the meals. Well, and the last one of the machine learning algorithm in this case is the reinforcement learning. There is type of machine learning where the algorithm learns to make some decisions interacting with the data of the environment of the data to achieve or to get to some different goals. So I'm gonna pass very quick in this slide. These are just some examples of different algorithms: random forest, support vector machines, gradient boosting, and artificial neural network that are used for regression or classification purposes. In clustering, you have k-means. For dimensional reduction, it's very common to use principal common components analysis, and for image classification or segmentation, but also for object detection, we have convolution and neural networks. That some of them are not called sometimes machine learning, and also called deep learning, depending of the kind of the algorithms. So in this slide, well, it's shown that it's a common workflow or flowchart, how these different algorithms or methods are used in the field of Earth observation and forest issues. In the case of using satellite images, we have this raw data or preprocessed data that we download, but we have to do a preprocessed data, sometimes deriving some different features, because if we are talking about optical satellite data, we have these values, for example, of reflectance, but we can derive the indices, vegetation indices or spectral indices, as Angel shown you in his speech. So you can preprocess the data, cleaning, deriving features, and these kind of things. After that, you have to split the data mainly in two parts. One of them on the right is for training this algorithm and to do an internal validation of the model. But you have also to keep some test data, and if this information is completely independent, is the best. But you have to keep it outside the algorithm to do it, to validate the model of the product at the end of the process. So we have this part of the training data, validation data. We put this information inside the algorithm to train the model. The algorithm learns with the information that we have given to it. So you can do after training the model, you have the results of the model, the estimations, the classification, depending on your goal, and you do a performance evaluation with the validation data that you have given to the algorithm. In this case, you can have a good result and you pass to the next step, or you have a result that you think that it could be improved. So you can go again to the beginning of the process and to do some different things with the data, to manage this data, to create new variants, new features, to get inside the model and to start the process again. But if you thought that this model is enough for your goals, you can go to the next step. Okay, that is, you can do a deployment, uploading this model to an infrastructure that it can be where it can be used, or you can go directly to the inference part or the inference step, that is applying this model that you have to a new data set. This data set have to be independent, it must have the same variables that you have entered to the model, and you, with this process, you get to the final product that could be validated or tested with the data that we have kept aside. And after the final product, you can do an analysis of the result. And if you think that this is not good enough, you can go again to the training model, adjusting the hyperparameters and do some different things to the model to get to a better final product. So sorry. There are some different validation strategies for models or for products. The first one, and that is very common, is the random holdout. As I showed you, you can split the data in training validation data and the testing data apart. And in this, you can see you reserve the training data set. Well, it's you can use whatever you want, but this is the biggest split of the data set to do it. Sometimes it's around 60% or 2/3 of the data that you have. You keep the validation data set to do an internal validation of the model, and you have the test data set to do an independent validation of the results of your model. Another typical or commonly used validation strategy is the CopPhil, is the cross-validation, the CopPhil cross-validation. And is commonly used to evaluate the performance, the learning model, also splitting the data set into different equal subsets or faults. Well, the model is trained in this number of different faults, and it's repeated k times, the number of times. The different, in this example, you have 4 times. And after all the iterations, the different models performance metrics are put together and can be averaged to provide a more reliable model statistical parameters. So the third one that I'm going to show you, there are a lot of them, of different strategies, is the bootstrapping. This technique is a resample technique. Is commonly used to estimate the distribution of the statistics, the mean or the variance of different parameters. Well, you in this strategy, you repeatedly sample the data with replacement. That is very important. This thing that the data is replaced sometimes. And well, if you want to keep something, well, the key idea is that you are simulating the different processes, and by the means of creating different data sets, and you have the independent statistics for one of the data sets, and after that you can do some things with the statistics to get a statistic for the whole model, like the mean of the statistics, well, depending of your goals always. So the good thing of this method is you don't need to assume that the data is in the distribution is not normal. You can use also bootstrapping to calculate the confidence intervals of your model, and it can also be used to the model evaluation. So we have seen here different strategies to validate the data, and I'm going to show you. I just want to show you. I don't want to go into detail in each one of them. Some different validated data metrics that they are directly related with your goal. That is, could be classification, regression, clustering, and others. And you can see some things. But what I want to show you is the confusion matrix. It's a method or a performance evaluation method that is used for classification purposes, and is used to evaluate the accuracy of the model's prediction. This matrix provides you with an insight, not just the overall performance result of the model, but also with the different kind of errors that you can have in the model. So on the left, you can see your observations. In this case, you have two classes, positive or negative. This is the observation. And on the top, you have what your model have predicted. The same classes, positive. And you can see here the true positive. When your model have said that the outcome is positive and the observation says the same. In this case, this case of false positive, your model have said that this is a false positive. Well, this is positive, but in the observation you can see the negative. And some of the validation metrics that you can use is the accuracy of the whole model, the precision, that is the proportion of predicted positive that are truly positive, is a measure of the quality of the model. The recall, that is the proportion of actual positive correctly identified by the model. In this case, is not a quality, it's a quantity measure. And the F1 score, that, well, is defined as the harmonic mean of precision and recall, and is balanced both equally between the different errors, but sometimes it could not be the ideal thing to do. So you can, depending on your goal, as always, I always say that depending on your goal, you can pick one of them and to choose wisely which kind of metric are you using. So I have finished here with the statistical part of the presentation, and now I'm gonna show you how we have used some of the algorithm or methods to generate 3 different products. I'm gonna start explaining a bit deeper than in the previous slides, the random forest algorithm. And I'm going to show you how we apply random forest to our first 2 products, the forest area and type and the tree cover density. And after that, I'm going to show you how we have applied a bit of the mechanics of the QSUM algorithm and how we have applied this QSUM algorithm to do a forest change model. So, random forest. Random forest is a machine learning algorithm. It's an ensemble learning method. What does it mean? That you are not using just a decision tree. You are using a lot of them, and is commonly used for classification and regression. It constructs different multiple trees during the training with different datasets using the bootstrapping methods. And the main idea behind this algorithm, random forest, is to combine these multiple decision trees to improve the overall model's accuracy, while reducing the overfitting compared to a single decision tree. That means that you are trying to get your model to a state that it can generalize the information that have inside. The different benefits that it have is the accuracy, the robustness of the model, but also that it gives you the a feature importance. That means that you can use random forest to evaluate the importance of the different features or the different variables that you are using as input to construct the model, predicting the target variable. And it's also very versatile, as I said, you can use it for classification, regression, and other issues. And how it works, it's a simple explanation. You have your original dataset, and you perform this bootstrapping, the bootstrapping method to generate different trees, and these different trees have different outcomes. So you have one prediction for each one of the bootstrapping samples, and after that, depending of the statistics of the different models, you have then this button and have a final prediction. You have this, well, for example, you have a classification between a healthy forest or a not healthy forest. So you have this classes, but also have this future important analysis, giving you the weight of each one of the features that you have used to train a model. So, as I said, we have used random forest to create these two products, forest area and type and tree cover density. Both of them are related. Is the same flowchart, as you can see in the outputs. If you follow this line, is the forest area and type map, but also after the feature engineering, you can treat the cover density map. That is necessary to create this product, the forest type map. So the objective, as I said, is to generate a forest type map at 10-meter resolution, spatial resolution. We have used 3 different classes. We are estimating or classifying the forest in 3 different forest classes that are closed forest, open forest, and mangrove forest. For this, we have used a set of 9,000 points extracted from very high resolution imagery, but we have divided this training data in 9 different land covers. So we are not classifying it here. These 3 classes, we are classifying these 9 classes. There are tree cover, mangrove. We are not differentiating here between closed forest or open forest now, but we have mangrove as an independent land cover class. We also have oil pan, grass and shrub, cropland, urban, versol, water, and wetland. These are the training data, the data that we are using to train this model, but we have to put an input data, this information from these different classes are going to be classified. This is the satellite imagery, in this case Sentinel-2. This is optical data, as Angel shown you before. The main problem with optical data here in tropical or close to the equator areas is the cloud cover. So we are using a composite for 1 year to avoid some pixels without data due to cloud cover. So we are also using more ancillary data. We are using a digital elevation model to generate some of the variables. And the main algorithm, as I said, is random forest, but we are using a conditional probability algorithm. I will show you later. So after gathering the data and splitting that, we have to preprocess the Sentinel-2 data to get the surface reflectant information. as I said, we are preparing a composite for a whole year. In the pre-processing, there are two main steps. That at cloud masking, we are deleting the clouds for each one of the images along the year, and after that we are performing we are generating this annual composite using the median. Why the median instead of using the mean? Because the median takes one of the real values in this time series. After that, we prepared the different variables that we are using, because as I showed you, we have surface reflectant information here, but we have to generate from this satellite imagery, the optical data, some variables. First one, some spectral indices focused on vegetation, but also with soil and water, different variables to approach the issue from different points. Some of them, well, we have used NDVI, it's a vegetation, MSAVI2, that is related with the soil condition, also the vegetation, and MVI that is related with soil parameters. And for the next version of the model and the product, we will also include some other indices like mangrove indices that have been so that very good and precise to estimate mangrove areas, but they will be included in the next version. We have also developed some textures, that is the entropy, closing and opening from the NDVI, as I remember well. What does it mean? This texture is the context information, is the relationship with the information that you have in a pixel and the pixels around it. These are some of the 3 parameters that we have computed. So spectral indices are the information within the pixel, and the texture is the information within the pixel related to the pixels around it. In the previous slide, I also showed you that we are using some digital elevation model. We have derived well, the elevation, the slope, and the aspect of the ground, and we have performed a feature selection based on an exploratory analysis and a collinearity analysis too. So for the forest and type, we have this is the modeling part. We have split the dataset in train, validation, and test subsets. We have persona hyperparameter tuning to get the best hyperparameters to get the best results of the model, but we have used an optimization functions to do it better and to do it quicker. So the model training phase has been iterative using the train and validation dataset. So for the forest area and type, this is the confusion matrix as I showed you previously. These are the 2 classes related with our product, the tree cover that will be split later in open forest and closed forest, and the mangrove class. As you can see here, it's a 0.9% of accuracy when the tree cover is classified as tree cover, and the observation is the same. And for mangroves is 0.98. And the other classes will be gathered together later to no forest class. It's like another class because it's different, having no data, that is, we don't have information, we don't know what is happening here, we cannot say that is forest, we cannot say that is not forest, but in this case we will know that this is not forest. We can say that this is not forest with the accuracy that you can see here. And I'm going to the previous one. Talking about this, I was talking about this part here, but we're going to take this way to the tree cover density map. So the tree cover density is defined as the proportion of the pixels covered by trees. Inside a pixel, as Angel showed you with the spectral analysis, the information within a pixel is sometimes representing different land covers. Could be, for example, trees and soil, 50% trees, 50% soil. So this methodology, we are going to use this methodology to estimate the proportion of in the proportion of a pixel that is covered by tree cover. And the methodology is based on the conditional probability. So tree cover density in this model, in this product, is expressed as the fractional vegetation cover multiplied by the conditional probability of the tree given vegetation. You can see here the equation. That is the fractional vegetation cover that is calculated here with the NDVI, the spectral indices of the NDVI, the values of the vegetation, the soil, and the mean NDVI of the pixel. So after this, we generate this tree cover density map, and we apply it here to the forest area and map, and according to a threshold of this tree cover density, we can separate. So I show you here the tree cover in a closed forest and open forest. And the results for the forest area and type product, you can see the very high resolution image on the left, and on the right you can see our product. On dark green, you can see the closed forest. In light green, you can see the open forest. And in violet, you can see the mangrove cover. And the other product is the tree cover density. You can see here, this is not a classification. This is a regression. You have values from 1% to 100%. So you can see here the different cover and comparing with the very high resolution image. Sorry. And now I'm going to pass to the next product. Is the forest change product, and this is based on a Q-sum algorithm, the accumulated sum algorithm. That is a statistical method that is commonly used in Earth observation, but also in other fields. It's used to detect changes or shifts in the time series data. So what we are doing here is a time series analysis. It could be used for land cover purposes, to analyze vegetation indices changes, or also or environmental parameters, but it's also used in other completely different fields like economics. So how it works? Well, it works by accumulating the sum of the deviations from, in this case, from the means, the deviation or the residuals or the mean over the time. As you can see here, in this graph, you can see that you have the time series of this parameter. In this case, is Sentinel-1, because we are using here Sentinel-1 in this project. You can see the different values along the time, and this line represents the mean of this value of the backscatter. And this line, you can see that the algorithm has detected a date when the change has happened. So you start accumulating the residual, that is the deviation from in this case, from this point to this point is positive, but from this point to this point is negative. You start accumulating. As you can see in this part of the graph, there is always it's always positive. So this is the accumulation until here that you start having negative values of the residuals, again positive, and the trend goes up, the accumulation. So the good thing of this method is that it's very sensitive, but sensitive to the magnitude of these residuals, of the changes, but also of the timing when it happens. So we have performed this accumulated sum, that is this line, but the next step is to estimate the magnitude of the change. In this case, is this amplitude. This is the magnitude of the change. So we have identified this as a pixel because we are using this method to analyze pixel by pixel. This graph represents the time series just for one pixel. So for this pixel, the time change, well, the candidate for a change in the forest is this. After that, you perform a bootstrap analysis. As I explained before, you get some different splits or subsets of the data, and you perform another graph, but you can see that the bootstrap curves are different, the amplitudes are different. So you set a confidence threshold to the values of this amplitude or the magnitude of this change for identifying real changes. So after that, you determine the change time, and you have a pixel that have changed during a specific date within the time series. Or maybe you don't have it because we have this example when it's happening, this change, but you can have another curve smoother than this one, and similar to the bootstrap analysis that is random. So you cannot say in this case that you have changed, but in this example we have it. So how we have used this method to develop the forest change algorithm. First of all, we have used Sentinel-1 data. Why we have used Sentinel-1 data instead of Sentinel-2, that is optics. Sentinel, as a reminder, Sentinel-1 is in radar data. When we started working to analyze for the proposal and for this, we saw that we have a cloud problem for the country, for the Philippines, that is, and if we wanted to do a forest change algorithm that can identify change in a short period, we do not rely our data source or we cannot trust a data source that could be covered by clouds. So we decided to use Sentinel-1 radar data. It has different problems, but we avoid this problem. So we are using Sentinel-1 data, GRD, and we are, as I said, we are performing a time series analysis. So we are doing the detection for 1 month. So we are, for example, we are detecting if there are some changes in the forest cover for the month of August. Well, for the month of June, that to be more clear here. But we are using the information, all the images available for this place from the 6 for the month of June and the 5 previous months. So we are using a baseline of 6 months. Why are not we using a longer period? That it could be more, it could be better, because the mean will be more representative of the cover, because the time of processing. So we had to decide to get to a compromise between the accuracy and the processing time. So we decided to do 6 months. The accuracy is good enough, and also the processing time is not very long. So the first step is the preprocessing of the images. I'm gonna go quick. So we do a radiometric calibration. We also perform a speckle filtering, and we also have a multi-look. The information that we have, the original information that we had is at 10 meters, but we are doing here the analysis at 30 meters of spatial resolution. After this processing, well, or as a part of the preprocessing, we also mask the land cover with the forest, with the previously calculated forest area map, just to perform the analysis for forest areas. So the main process is the application of the algorithm to the land, the Q method. But as an iterative process, we selected the best parameters to fit that, like this threshold that we are setting here. And after that, we have a map of changes, but we also wanted to perform to clean the output, a topographic correction, because Sentinel radar data has some problems with some slopes, tree cover density correction too, and we also used a majority filter and a sieving filter to not getting some, to avoiding having some noise in our results. And we wanted to, I'm gonna go back. Well, sorry about this. We wanted to get to have this statistic, the true positive, to if we have in our product that a pixel has changed, that it's true, instead of having this parameter. So we have used this to estimate the values of our product. So now this is the forest change result. You can, this is a very high resolution image too. You have an image is on the left of June 2020. Sorry, and a July image for 2022. You can see here that it has been some kind of deforestation. In this case, it's deforestation. It could be also a fire, and we have detected. And you can see that it doesn't fit perfectly to the sun, but it's very useful to detect when when the change has happened, but also to where the change has happened. And we wanted also to show you some limitations about our three products. Well, the first one is just, well, it can be applied to forest area and type and tree cover density, is the dependence of the model on ground truth data. We have used here, we haven't used ground truth data directly. We have used some observations on very high resolution imagery of the different classes. We have extracted the different samples from very high resolution images instead of using ground truth data because it wasn't available for us. The next of the limitation is the data quality and some sensor limitations. For example, in the case of the forest area and type and tree cover density, they are created using optical information. So we have some cloud cover. We have used a year trying to avoid, but sometimes we can have some pixel with no information because this pixel has been covered by clouds all the data the images have been taken during the time series. And also, but we have problems, issues with data quality and sensor limitation with the radar data. So I told you with the different slopes of the terrain, and also with the moisture of the terrain. It could be, it's not necessary, but it could be some generalization and transferability issues, or models have been trained and prepared to this specific kind of vegetation, this specific kind of forest. So it cannot be transferred to, for example, to a Mediterranean forest here in Spain or in South Africa or in Australia. And also we have limitations and we have some processing constraint. To process this model takes some time, takes some hours. If we didn't have this limitation, we could perform this forest area and type and tree cover instead of annually for 6 months, but we cannot do it. And if we don't have this processing time issues or constraints for the forest change, we could use longer temporal series that would be more representative of the forest conditions. So I have finished with our products, but I want to show you briefly other forest applications that we have developed in our division previously for other projects or for some studies. I'm gonna be very quick in this part. So this is another example of forest type classification. The input data here was the same than in our product. Is Sentinel-1, and we are classifying here the dominant forest. This is an example for Portugal, if I remember well. This is another example also for Portugal, but we have in the previous one we have used random forest 2 and the ground data is forest inventory, and this one have the same input data, the same method and the same ground data is a forest inventory. In this case, no ground data, but we are seeing here these maps of probabilities. In this case, this is in the blue, if I remember where is eucalyptus, and is in. And in red we have this forest on the sides of the river. Well, in this product or in this project, we located bone scars, but also clear cuts. You can see here the bone scars. Here we have also used Sentinel-2 and random forest because random forest is very useful to this kind of matter. But in this project, we have ground data that was provided to us by the user. So there are different. This is also for Portugal too, I think. In the case of deforestations, in this case we have used Landsat and Sentinel-2 information from 2 different missions, 2 different satellites. Both are multispectral, but they have some difference between them. And the method that we have used here is a time series method, time series analysis method. This is CCDC, is the continuous chain detection and classification. But we have also used here a light GBM that is similar. Similar to random forest, but has some advantages comparing to random forest sometimes. And also the ground data was provided by the user. And this is a study case for Peru. I've been showing you some products related to the forest change, but in this case I'm showing you this it's a different product. This is related with carbon estimation or some parameters related with carbon. This is a case for Spain. So we have also used Sentinel-2 from Copernicus. The method that we have used in this case is not a machine learning method. We have used empirical equation, and the reference data, the ground data, is from a biomass inventory. And on the left, you can see the map of above ground biomass classified in different thresholds, but also you have a map of carbon stock on the right. And this one is not related with the structure, as this is the biomass, and not related with well, it's a bit related with changes in the vegetation. It's from a pest detection. It's directly related with forest health. The method that we have used here is the multi-temporal regression, and the ground data that we have used for its inventory. And we have also another one here related with forest health issues. In this case, we have used random forest, and this is for Central Europe. And well, I have finished with this information. Thank you very much for your attention. Patricia, I think it's your turn.
Yes, thank you very much, Pablo. I think you cannot see me. Ah, now, finally. That's good. Okay, so thank you very much, Angel and Pablo. I think my colleague gave a great training session, so thanks so much, and I hope you all enjoyed it and learned a lot about remote sensing applied to forest. So we are in line with the agenda. So the last part we will go to show the questions that we have prepared for this last part of the meeting. I will share my screen again. Let me 1 second. Can you see it? I will share the link again just in case in the chat so you can access to the Mentimeter tool again. So this will be is basically the same questionnaire that we have earlier, but now I will show the last 4 questions. So I will show it here. I hope you can see it. Well, basically, we would like to know if the course meet your expectations, and based on the objective that we provided, based that the aim was to provide a theoretical training related to the remote sensing and the applied artificial intelligence for forests in relation to the CopPhil project. So that's perfect, basically. Expectations are met for all, so that's good. Happy to see it. Let's see if we get additional. Okay, that's something that we have further contributions. So I will go to the next one. Well, here we would like to know which part of the course did you find most useful. Here we have the 4th main section of the training, the principle and data when Angel explained like the basic of remote sensing, then the basic and also the sensor. Then my colleague Pablo explained the main aspect of the data analysis for forests. He explained later the CopPhil forest products, and he finished with the other potential application for forest. You can press more than one if you find that you find most useful several of them. So this also will help us to know if we need to go further in the next training session in some of the aspect or in other. So thanks for that. We really appreciate your participation and your contribution to these questions. Also here, we would like to know, is there any specific topic that you would like to be covering more depth in future courses? As I explained at the beginning, this is the first one, is focused on the theoretical aspect, but we will have at the end of May one on-site training in the Philippines that will be more practical. We will show how to use the forest products that are integrated in the CopPhil system that will be integrated in the filter infrastructure. We will see another sample, another exercise that can help you to go more in deep in a practical way in this topic related with the remote sensing and the artificial intelligence for forests and some demo. That's training, yeah, it's good. Also, if you want to let us know anything after this session by email, that would be great as well. Okay, that's perfect. Configuration for change detection. Focus on pest detection and monitoring. Okay, it's something that we can see if we can provide. Okay, thanks for the comment. Okay, so as I said, we are totally open to receive any other suggestions for the next trainings. Also, we will have the last one in August, more focus on applications, station index and mapping species. Okay, see if we can tackle it. Is to cover Bascata and others. Okay, that's, I think, good inputs that can be very helpful for us to know how to tackle the next session. That's good. Okay, so I will go to the next, the last one indeed. If you have any other comment, also you can provide it in the chat. And well, this is just a final question. If you want to say anything about the training, please, you can type here whatever you want to tell us about the training. This would be very useful for us. Thank you. Thank you to all of you for your participation. Thank you, Carla. Thank you, Ash. Many thanks to all of you. Happy that you enjoyed it. You will have the content of the course in the platform. I don't know, Carla, if you want to say something about how to access platform and something like that.
Yes, so just to continue with that, so thank you everyone for staying with us through the full session. So we hope that this full training really gave you the full solid foundation for the forest monitoring, and the materials will be available on the CopPhil Digital Campus soon. So I will just briefly show. I think everyone here is also the same applicants, training participants for the last courses. So we're going to be releasing the forest monitoring course page. So you have all the details here, and yeah, The team slides are here, all complete. You can download them if you want to revisit some items that they've discussed. And then the video recording will be made available soon. And for the certificate, you just have to finish the training feedback form and the short quiz to get your certificate. So yes, all details here. And yeah. So Patricia, do you want to add more things?
No, I
Okay.
have nothing else to add. So
Mm-hmm.
just to say again, thanks to all of you, and I hope you enjoyed it and keep going. We will see each other in the Philippines in 2 months.
Yes, so we encourage you all to stay tuned for the next part of the training series. You will receive also the invitations and when the next ones would be, and there we'll explore the practical and application aspects of forest monitoring. So if there's no more questions, thank you again for your time and participation. So thank you, Patricia, Pablo, Angel, and to everyone. See you all in the next sessions.
Thank you. Bye-bye.
Bye-bye. Thank you so much.
Thank you. Bye.
Thank you
Bye.
all. Goodbye.